In the last video, we introduced the Buckingham Pi theorem. And the Buckingham Pi theorem is a way to generate dimensionless groups from a list of dependent and independent variables. So if you recall, the example that we did in that section was the drag force per unit length on an airfoil. So remember, this F primed here was the drag force per unit length. And we started off the Buckingham Pi process by saying that that drag force per unit length depends on these four variables: density, dynamic viscosity, velocity, and chord length. And we went through the whole Buckingham Pi process and we found a non-dimensional form of this function. So we found a drag coefficient on the left and a Reynolds number on the right. So the whole idea behind that was we reduced the number of parameters that we need to describe this phenomena. So I just want to return to something that we talked about in the introductory lecture, and that is one of the motivations for doing dimensional analysis. Let's say that we were going to do a series of experiments to measure the drag force on a new type of airfoil that we had designed. So if we look at that problem from this point of view, so we want to do a dimensional presentation of our numerical results, we look at this and we say, well, that drag force depends on all of these things. So to fully understand how the drag force depends on these things, experimentally, I'm going to have to do a bunch of experiments where I change these four things and I see what happens to the drag force. So you might set out to do that. So you might start off in a wind tunnel and you say, okay, we've got an air flow here, so the density and the viscosity are the density and viscosity of air, and you might take a particular size of an airfoil, your particular design you're investigating with a particular chord length, and do a whole bunch of measurements of drag at different velocities. You would probably do a lot more than 3, but this is just representing how you might present that data. And so you want to know, how does the drag force depend on this C? So you make an airfoil that is a little bit bigger, still the same shape because you're investigating a particular shape that you design, but you just scale everything up and you make a larger airfoil. And so you get a second set of measurements of drag force. So every cell in this table you would be filling in with a force measurement. So this table would show you how force changes with chord and with velocity, with the density and viscosity kept constant. So you'd have probably a very, very large table of measurements like this. And that's one way you could represent your experimental results, is a tabular set of data like this. Now you could possibly fit a curve to this data so that the force is expressed as a function of V and C, but of course that curve would only be good if the density and viscosity were the same as your measurements, in other words, were for air. So quite often though, when we're investigating a new design like this and we want to know forces on it, we might actually do the measurements in a different fluid than air so that we can vary the density and viscosity and see what effect that has. So we might also make measurements in a water tunnel. And so we would have a different density and viscosity. We would take different chord lengths, run the water tunnel at different speeds, and again make a whole series of force measurements. So to give detailed experimental results, we could end up with some very, very large tables of numbers, or we could end up with a whole bunch of plots or functions that are fit to these tables of numbers. But it's actually quite complicated to present the experimental results because there's quite a number of variables on the right-hand side of this equation. Now this is actually a relatively small set as well. We could add a lot of other variables to the right-hand side if we were interested in looking at other effects on the drag force. So this is the situation if we were going to present our experimental results dimensionally, or just based on this function right here. So now we take a look, what would happen if we did the dimensional analysis, we applied the Buckingham Pi theorem, and we used the results of that Buckingham Pi theorem to present our results in a different way. What would that look like? Well, this is what we learned from doing the Buckingham Pi theorem, that the drag force, the dimensionless drag force, is a function of this single parameter, and that's the Reynolds number. So now, to represent this function, it's a function of only one thing. Certainly that one parameter, Reynolds number, has 4 different things in it, but the important thing is how the Reynolds number varies. Not necessarily how any individual one of these things varies, but how the Reynolds number varies. So notice, if we doubled the velocity and cut the chord in half, the Reynolds number would stay the same. So what Buckingham pi theorem is telling us is that the drag coefficient will not change. So if we take an object, we double the velocity and decrease the chord by a factor of 2, the Reynolds number is the same, therefore the drag coefficient is the same. Okay? We're not saying the drag force is the same, but the drag coefficient, the dimensionless drag force, has to be the same. So this also allows us to present those experimental results we did in a much more compact way, because we've just got drag coefficient as a function of a single variable. So we could plot that or give a very, very simple table of numbers. So this is just a cartoon sketch. It's not the drag force curve for any particular airfoil design, but it's just illustrating that we can present these results in a very compact and a very, very succinct way when we take advantage of numerical analysis. Now, the other thing that this has application to is planning our experiments in the first place. Before we've done any measurements, we want to do this analysis. And this will tell us what we need to do is vary the Reynolds number to investigate what this curve looks like. So we need to take drag force measurements for a whole bunch of different values of this. So we would look at this and we would probably ask ourselves, well, what is the easiest one of these things to change? Well, the velocity is the easiest thing to change. Density and viscosity are actually very hard to change. We've got to do our experiments in a different fluid. Chord is kind of hard to change. You have to machine or 3D print a whole bunch of different versions of your airfoil, whereas velocity, you just have to change the speed in the wind tunnel. So V is a very easy thing to change, so that's probably what you would do. And so dimensional analysis is telling you you're actually wasting your time changing all of these other things. You can just vary the Reynolds number by changing the thing that is easy to change. Okay? So that's a very powerful use of dimensional analysis in planning your experiments. So the other thing we want to address in this lecture is what happens when we add some more parameters on the right-hand side of that equation. In other words, when we add more independent variables. So what we're going to do is still look at the same cases, the forces on an object. So instead of looking at a two-dimensional airfoil, we're going to look at a finite wing. So this is a wing with a certain length, and we call that length the span. So this S is one new parameter that we're going to be bringing into our analysis. Now, instead of talking about the force per unit length, we're now also going to talk about the total force on this object, talk about the drag force on this object. Now, as the title implies here, the other parameter that we're going to bring in here is the angle of attack. So the angle of attack in aerodynamics, if you take a line that joins the tip of the airfoil and the trailing edge of the airfoil, so the leading edge and the trailing edge, that's what this blue line is, and the air is approaching the airfoil at some angle to that chord line, that's called, then that's called the angle of attack. And so we're going to call alpha here the angle of attack. So notice we're going to do a very similar analysis to what we did before, only we're adding two more variables. And these are independent variables we're adding, because we want to know how does the force on this object, the drag force on this object, depend on the density, the velocity of the free stream, the dynamic viscosity, the chord length, and now adding to that list also the span S and the angle of attack alpha. So our two more variables show up here. So these are the two things we're adding. All the rest of this is the same as what we did before. So we're not going to go through all of the details of Buckingham pi theorem right from the beginning again, and there's really no need to do that. If you want to add new variables to a Buckingham pi analysis that's already been done, there's no need to redo the work that you've already done. So we're not going to do that here. So in this analysis, we're still going to select rho, v, and c as the repeating variables. Okay, and that's key. If we actually picked one of our new variables as one of the repeating variables, then we would have to rewind and do most of the Buckingham pi theorem over again because we'd have a different set of repeating variables. So we're going to pick that same set of repeating variables that we used when we first analyzed the drag force on this object. So we have these repeating variables. So our n is now 7 because we've added on 2 independent variables. Our j is still 3. The new independent variables we added haven't added any new dimensions, so j is still 3. So now we expect to get 4 dimensionless groups instead of the 2 we had in our first analysis. So the pi 1 and pi 2 are going to be exactly the same as before, because if we have the same repeating variables, we're going to get exactly the same results as before. So we're not going to redo pi 1 and pi 2. So pi 1 will be our drag coefficient, pi 2 will be our Reynolds number. But we will take a closer look at the 2 new dimensionless groups. So pi 3, again, how do we generate pi 3? Well, we have our same 3 repeating variables to these 3 unknown constants. We take one of our new parameters, and here I've chosen the span, s, and we go through the same process as before. So we represent the right-hand side of this equation in terms of its dimensions. So again, density, velocity, and chord length. And then the dimensions of our new variable here are length. So again, we form 3 equations with 3 unknowns by adding up the exponents of m, l, and t. And so those 3 equations, it would tell us right away that a is 0. So go back here and notice the only place that m appears is in the density with this particular set of variables. So if the only place that m appears is in the density, then this a has to be 0, so that density will not be a member of this pi group, because there's no masses in any of this other stuff to cancel out the mass in the density. So a is 0. And that comes about through our procedure that we talked about, because we would have an equation here that just says a equals 0. So our first equation just tells us a equals 0. Actually, the same thing happens to b. If we look at this, velocity is the only place that time occurs. So a and b are both 0, and our d is -1. So we get our dimensionless group is just s over c. Notice that this parameter that we've added has dimensions of length, and one of our repeating variables also has dimensions of length. Well, whenever that happens, these other things are going to drop out, and the resulting dimensionless group is just going to be a ratio of these 2 things. So it's just a ratio of 2 length scales in the problem. This happens to be the chord of the airfoil and the span of the wing. Okay, so the resulting dimensionless group here, pi 3, is just a ratio of 2 dimensions. So if we were to go on and we were to add other physical parameters, other dimensions of this airfoil, like perhaps the curvature of the leading edge or the amount of camber, which is how much the whole airfoil is curved. If we were to add other descriptions of this airfoil that are described by a length of some kind, then the new dimensionless group that comes out would just be a ratio of that new parameter divided by the chord length. So because the dimensions of both of those are length, that would be a dimensionless group. So that's one thing this example is intended to illustrate, is whenever you add a new parameter which is a length, then the new dimensionless group is just going to be a length scale. So that length divided by, in this case, the chord length, or whichever one of your repeating variables has those same dimensions of length. So that's pi 3. Now pi 4, the other reason that I've chosen this example is if we go back and look at the other variable that we added, we realize it's the angle of attack. Well, what are the dimensions of an angle? Remember our 4 fundamental dimensions: mass, length, time, and temperature. Well, what are the dimensions of the angle alpha? Well, alpha, an angle, does not have any dimensions. So our alpha is already a dimensionless number, so pi 4 in fact is just equal to alpha. If we wanted to go through this whole process here of writing this all out, we could certainly do that, but there's no dimensions here, so A, B, and D all have to be 0. Okay, so pi 4 is alpha because it's already a dimensionless number. So that's another thing that we can use to do our Buckingham pi theorem a little bit quicker. If any of the independent variables that we decide are important in a problem, if they are already dimensionless numbers, and an angle is a good example of that, then they just go directly into the list of dimensionless groups, and we really don't have to go through the process of Buckingham pi theorem, through the process of solving this system of linear equations, because it's just going to tell us that all of those exponents on our repeating variables are 0, and our dimensionless group, so-called, is just that parameter that we introduced into the problem that already has no dimensions. So just to help you realize that an angle is a dimensionless number, think about this little sketch here. Okay, so I have a little segment of a circle. So there's an arc here, an angle alpha of some kind. This is a radius, and this L here is the arc length. Well, realize what an angle is. An angle is actually a ratio of length divided by radius, right? That's what an angle is. So it's actually already a ratio of two distances. So it is a dimensionless number already, alpha. So with these two new dimensionless groups, then we can express our new functional form. So we have our drag coefficient here as a function of three dimensionless groups now. Our Reynolds number, as we got before, but our S over C ratio and our alpha. And this is called the aspect ratio of the wing, a very, very common parameter and a very important parameter in aerodynamics. What is the aspect ratio of wing? Some aircraft have very, very long, skinny wings. Gliders are a good example of that. So they have a very, very high aspect ratio. And other aircraft have very short, stubby wings. And aircraft that carry a lot of weight tend to have short, stubby wings, and so they have low aspect ratio wings. So this is our new dimensionless functional form. Now, as happened the first time we did Buckingham pi theorem on this particular application, we did a few group manipulations to get these in a more familiar form, and we're going to do that here as well. We're going to take this first group, which is going to be our drag coefficient here eventually, and we're going to combine it with this group and replace this with the result. So that looks like this. So notice I'm taking this and multiplying it by C over S. So I'm combining it with this one. So I've inverted this and multiplied it by that. So notice each of these things is dimensionless. So when we multiply them together, it's still dimensionless. It's still a valid dimensionless group. So when we multiply these two things together, the C there cancels with one of these C's, and we get F over rho V squared CS. Well, this CS is the plan form area. So if you're looking straight down on this wing, it's the area that you would see called the plan form area. And that's a very common physical parameter of the wing that we would use to define the drag coefficient. So the last thing we need to do to this is multiply by a constant, and that's 1/2 again. So we get our drag coefficient here is the drag force divided by the dynamic pressure, 1/2 rho V squared, multiplied by the plan form area, CS. So that's how the drag coefficient would be expressed in aerodynamics. Now notice here, I haven't put a D on this. We could have actually investigated any of the forces on this airfoil, and we would have got exactly the same result. So if we want to look at the drag force, then we would non-dimensionalize the drag force with this quantity and call it a drag coefficient. If we wanted to look at the lift force, we would non-dimensionalize the lift force with exactly the same quantity and get a lift coefficient. And of course, the drag coefficient and lift coefficient are two really important parameters in aerodynamics, and you want to think of them just as dimensionless drag and lift forces. So that's the end of this module of the course, and it's taught us a way to take a functional relationship between a dependent variable and a whole list of independent variables and write them or represent them in a much more compact way by using the Buckingham pi theorem. So like I say, we'll be using a lot of these dimensionless groups in the next module of the course on turbomachinery. We'll see you there.